Okay, so lecture 16 is going to be a special topic on applications of the statistical method that we talked about in the previous lectures. And we will look at a special set of data, which is the COVID-19 pandemic data. And we'll see how we're going to visualize the data and do some modeling with the data too. So in the last lecture, we learned basic concepts of correlations, covariance, and regression. And we learned how to fit a linear curve and nonlinear curve. And we also talked very briefly about how to understand the quality of the fitting using the Peikoff parameter. Right. So in this lecture, we will apply the knowledge we learned in previous lectures to analyze the COVID-19 pandemic data from the internet. And these skills will including program control, if for loops and NumPy arrays, pandas data wrangling using the data frame, and also regression, curve fitting for predictions. So the COVID-19 pandemic is an unprecedented global public health challenge, which nobody expected. So the governments of the world, everybody publishes data online, and people gather the data together and generating these nice graphics showing you the evolution of the COVID-19 crisis. And you can see that this is a world map showing you the distribution of numbers of the total confirmed cases. And this is a line curve, which is called time series analysis, a time series of the COVID-19 cases. And this is actually geospatial data analysis. So to understand what's really going on and possibly predicting anything in the ballpark, and the data is the key. So here is a list of sources of data that's available online, and you can find from all these websites getting data. And if you look at the nice website with interactive maps and also a data project from Johns Hopkins University, and you can find it right here. And then these are the other data sources available down here. And the steps to get the data first, and we're going to look at what I did here this time is I got this website called outwardindata.org, coronavirus. And if you go to this website and you find these images, and you can actually download the data right here. So this is basically a page telling you the total confirmed COVID-19 cases. And if you click this tab, and you can download data right here. And then this is another data file with total daily and converted cases. So today we're going to look at how to generate a plot like this and also do some analysis based on, this is called time series analysis. And next week we will learn how to generate a map like this using geospatial data analysis techniques. Right, so this data is from this website, but it's originally from the European CDC. So first one, so when we download data, and the first task to do is to load the file into a data frame, which you've already learned how to do it. So so we need pandas, we need NumPy, and we need matplotlib.pyplot for plotting. And then if some of you may already notice that I have this codes here to try and to ignore the warning, so there's no warning message. Python does give me the plots, give me the data frame without warning me something's possibly wrong, but it's actually not. All right, so this is a file name, and pay attention to my directory here. So I have // means I go one level above my current folder, and there's a folder called datasets, and inside folder there's a CSV file called total and daily cases COVID-19.csv. So I do pd.read.csv. It's not Excel file, so it's read CSV. And if you look at the head function, and this is basically the data frame I get. I have columns called entity, code, which is a country, and code is also the country names, and date, which is string, telling you what dates are, and total confirmed cases, and also daily new confirmed cases. Right? So you see that it's pretty much there, but something is annoying. One is that the column names are too complicated. And the second one is date column here is basically a string. So we need something that numerical of the date we can work with. So the first thing that we do is we change the column names. If you still remember in pandas, how do we change the column names? We do column.rename and columns equal to a dictionary. So I change the old name to new name, old column name to new column name. And in place equals true because I wanted the changes to be effective immediately. Right, so if you look at df.head, and this is basically the data frame I got, and you can see now this column is changed to total cases, and the other column is called daily cases. So that's the new cases every day. That's the accumulative data, at this particular date. All right, so now next step, let's add a date information in the data frame. So this is something new, but very useful. And I'm not going to go into too much details. I'm going to show you what I did. And if you want more information, you can find it online. I will tell you where it is. Right, so that's actually getting information and learn it based on your own skills, search or asking questions or trying to find examples. And that's exactly the way how you learn Python, right? Okay, so the modules we need is time and also date time. So from date time is a default mod. It's a basic module of Python. So you don't need to install it. It's just like NumPy. Import date time and time delta. So now the first thing we do here is import these modules. And now I'm calling a function from pandas, which is pd to date time. And remember that the date is a column that with the string variables of the dates. And I changed the dates, convert the dates to a date time module, which is one of this object like this. And then I give a name called dt. And then if I look at the head, now I have a new column called dt. And you can see now December 31st, 2019 is changed to 2019-12-31. So this is a numerical value and this is a string value. This numerical value is special because it's a date time object that you can do plus, minus, divide, and even do all these numerical calculations with the date. Right. So now there's a new data column called the DT, and they're actually date time objects. And you can do date time manipulations with this column. And then you can find a full documentation here. If you're interested, take a look at it. All right, so now let's find out the dates starting from December 31st, 2019. So these are with date slots. It's nice to have all these dates, but sometimes we want to just date starting from this. Let's say we want to call this date 0 and this date 1, this date will be 2, this date will 3, and so on and so forth. So how we do it? So first of all, we push the column dt into an array called date. So now date is basically this column. It's a date time object. All right, now we said that the 0 time is called date to 0. That's the starting time. And that's a particular syntax use a function from date time called string p time. So string p time is 2019-12-31, and that's year, month, date. This is the format. So after we did this, and now we can do subtraction, which means that if I want a new array, which is called days, so the days with the first row will be this date minus exact this one. So I use the map function here. So I do date map, and there's a lambda function here, means that lambda function and x, now x, each x will be one of these, and x minus the 0 date, which is December 21, and dot days. So so do the map function. I'm mapping all the date time in this dt column to be the days between the current date x and the date 0, and I want the days, right? If I do this, this is the start time, and this is basically the trick. You map every date based on the 0 date and subtract the 0 dates to get delta. And then this is now I got new column, got days, and it's 0, 1, 2, 3. So it's a nice time series starting from 0 where the data starts. And that makes the analysis a lot easier, right? So try to play with this and see if you have problem understanding that. It's pretty straightforward. All right, so the next task, now we got the dates. We got days since the onset, and then now we got the total cases, daily cases, and we can generate a time series of the total cases or the daily cases, right? So here, I'm gonna introduce a new type of plotting using the date frame dot plot, which means that you can use the data frame dot plot and column horizontal column and vertical column and do all these options, right? So now let's try to look at this. I want plot the total cases as a function of days, right? So here, first of all, let's do the data filtering. Right? If you remember, this data frame has all the countries. If you just do df.plot with this, I got thousands of lines because every country will be there. So to make things easier, I want the total cases over the world. So there's a one entity called world. So we do df.entity equals to world. So now I'm selecting only the world dates with the data. And then now this data frame only has the entity world. And I do plot total cases as a function days. So x days is the x-axis and total cases, that's the y-axis. And now this is the data type and this is the title and y limit and x limit. So x limit is basically the maximum days, right? So if you do that, you get all these options and you can take a look at, compare with this default, and these are the properties, and then you can get a plot like this. So this is days, and that's the cases, and title is total cases, and you can see it's growing really fast, almost like exponentially. But I would say it's probably more linear at this moment, right? So you can also do the same thing, use plt.plot. That's something we're familiar with. So you'll do plt.plot df and df.entity equals to world.days, and the same thing total cases, and then you plot the title, x label, and limit, and show, you get the same plot here. So that's just another way of plotting the data columns in the data frame, just using the data frame.plot function. All right, so in this case, you can also plot the function. Remember that in the previous plot, we plot the function use days, which starting from 0. So because we say December 31st, 2019, that's the onset date, which is 0. But we actually have the real dates of that. So you can also plot dates, which is the DT, down here. And then you can see that if we plot the total cases as DT, and we can get a function like this, we can get a plot like this, but now the horizontal axis has actual dates separated by weeks down here, which is fairly nice, right? January, February, March, and DT, and then the curve. And then the thing different here is I used log y equals 2. I'm changing the y scale to be logarithm. So now it's from 10 to the second, 10 to the third, 10 to the fourth, 10 to the fifth, and then goes like this in this case. Right? So it's the same idea, use plot, but you use, if you use the plot and df.dt and the df.total cases, and you get something similar, but you get actually the full date. And so the dates are quite the same dates, but the layout is different. So pay attention to the differences. If you're plotting the horizontal axis, you use the actual date, right? So now we can also put total cases versus time in a plot with more data together, right? So for example, if you want to look at the data of China starting from January 1st to 2020, and we get the starting date equals to that, and we do the filtering. Now the entity equals to C. Well, C here is China. So the reason I'm using C here is because you can just change it here, or you can loop it over with C, right? Entity equals to China, and time, date, dt greater than date 0. Right, so now this is going to be the new data frame. So I'm now plotting the dt as a function for the total cases and daily cases as a function of dt. And the total cases, I'm using a line plot, and the daily cases, I'm using bar plots. And then I do the same labeling, and also I rotate the x takes 45 degrees, so it's a little bit easier to see, so the date labels don't get clustered. So you get a plot like this, right? So the total cases is the line plot right here, and these bars are the daily cases. And you can see these are the DT labels, and that's basically coming from DT. I rotate it 45 degrees, so they kind of separate it nicely, right? So you can see that before March 10-ish, and most of the cases here are domestic. And that's when you have the outbreak, and mostly inside the country. And after that, you see a growth in the daily cases, and these are actually where you start to have imported cases because the outbreak starting outside. All right, so we can also put time series on the same plot, multiple time series on the same plot using a for loop, right? So now here's the example what I did. Here's that if I want plot to the countries, like the 7 countries, China, Italy, United States, Spain, Iran, South Korea, Japan, and I want plot all these countries' total cases as a function of time in the same plot. So you do exactly the same thing starting from January 1st, and then I create a figure. So now what I did here is I created C, which is an iterator variable in the countries. The countries are list. So C is going to step through all these countries. And now first I filter the data frame to get the country equals to C and times equals to time 0. And then with this new data frame, I do the plot dt as a function of total cases and use a circular marker, and label is basically country. So what happens here is that I'm looping over the list of countries, and remember that dt is the date time object down here. And then now I can do comparison dt greater than dt0. So dt0 is January 1st, 2020, right? So after that, and you get a plot like this. So this is the results that China's got, and you got other countries like Italy, United States, and all these all the way to Japan, which follows a very, very less aggressive curve, while these are more on the exponential growth. All right, so this is a nice way of you can loop over this one, and I hope you understand how to do this with the for loop, because some of you usually do these plots by just copy pasting the lines of code. So if you do that, and you will need 20 times more of code, 10 times more of code to do this, but for loop, it's only 3 lines of code. So the key here is create a variable iterating over the list of the countries and change the country and then do the plots. Right, so these are setups that's straightforward. So we can also set other criteria. For example, I specify the 7 countries that I want to look at, but now if I want to look at countries that has confirmed cases greater than 10,000 in this case, so the same idea. So I need to loop over all the countries and then find out the countries that has cases greater than 10,000, and I want to plot those ones. Right, so how am I going to do it? So first I create a set using the entity column, right? So df.entity give me basically the column, all the country names, but they have duplicates. So what I do with the set is, because if you remember that set elements in a set is unique. So after you do convert all the entity column to a set, only the unique country names are left in this way, right? So it's the same idea, use a numpy np.unique function to do the same, but set is relatively easy to do if I don't care about the order of the countries. So starting date is, now I'm changing a date. Starting date, it's not used. This is not used here. So I create a plot. Now I'm looping over all the countries and I'm trying to plot it. But there's a condition. I plot the curve of the country, and that condition is the number of total cases has to be greater than 10,000. So how am I going to do it? So first of all, this is the selection of the country. So df df.entity equals C. So C is going to be countries in all the countries. So say C is China here. So now I'm getting the df with the columns that has China in it. And then total cases, that's the total cases of of China. And max is basically the maximum number of in those total cases, which is the most recent number. And then if the max number is greater than 10,000 and C is not world, if it's world, if you don't do this, and you have another curve, which is the sum of everybody, right? So here I have two criteria. One is the cases is country C has maximum cases than 10,000. The second one, the country C is not world, right? So if both of criteria are met, and then I do the filtering by getting the data, DFC is basically based on select based on the country, and then I do the plots at total cases as a function of DT and label it as C, right? If I do this, and then you can see that this is kind of a plot that I get. You know, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 countries that has total cases more than 10,000 up to March 30, which is a lot in this case. Right, so look at this. This is slightly different with the previous slide because I used a linear case in this linear scale in this way, and you can change it to logarithm. So the point here is that how you select data sets to plot with criteria, right? One is country, and the other one is how many cases. And the previous one is also what's the date, right? You want a date after some particular starting onset time. Okay, so the next part is that now we have learned how to plot the results as a function of time, and then we can also fit the results to a function to make regression. And if you remember that regression, we want to do some predictions. Maybe they're good, maybe they're not, right? But you can always do it. So if you still remember that the curve fitting, so we're going to use curve fitting, and this is an example of a linear curve fitting. So what you do is that you first create a linear function, which is called func linear ax plus b, and then we use the curve fit from SciPy and do the linear function and with the x data, y data, and then we plot the function, use the p-opt. P-opt is the optimal fitting results for A and B. And you can see that we did a linear fitting, which works about right. And we did a quadratic fitting, which works even better. But if you still remember that a quadratic fitting fails to predict when the winds are greater than 100 because it drops down, right? So let's take a look at the fitting the data in the linear in different forms of functions. For example, if you want to fit the US total cases, use a linear function, y equals to ax times ax plus b, x is the time. And then let's say we start fitting the data from March the 1st. Now I change the data 0 to be March 1st, and I filter the data first, create a new data frame called df underscore US equals df entity equals to C, and time greater than date 0. So now I create a new variable. Remember that I could use the days directly, but remember that the days will not be 0 starting from March 1st, because 0 is the last day of 2019, right? So now I create a new NumPy array here, and if you look at the days, it will be starting from 62. Yeah, that's df.us.head. And then if I use the days, it was starting from 62 to about 150, and which is not so great. So let's say I create a new days array, which goes from 0 to the date right now. So it's df us dt.size, so that's the length of the column. So it's from 0 to the column length minus 1. So that's the same length as total cases. And if you do this, and I can plot days as a function of df underscore us total cases, And you can see now, starting now, the horizontal axis is 0. And then if you read the label, it's actually days after March 1st, 2020 here. So 0 means March 1st, March 2nd, and then 1 means March 3rd, and so on and so forth, all the way there, right? So now let's fit this curve as this is the X data, and that's the Y data, see what kind of functional form fits that. All right, so the fitting is actually exactly the same as what we talked about previously. So first of all, we define a linear function like this, ax plus b, and now we fit the function, use the curve fit. And remember, the curve fit comes from scipy.optimize. And what's the function form? It's called func linear. And what's the x-axis, which is days? And what's the y-axis is DF-US total cases. So DF-US is actually the US entity equals the US and date after March 1st. And then if you do that fitting and you plot the data and the fit function together, this is what you get, right? So the blue dots here are data, and you can see they grow like this. But if you try to fit a grow like this to a linear function, you get something like this, which is ridiculous, because the total number of cases is minus 25,000 at day 0, which is non-physical, right? So that's bad, which means that you can fit the function mathematically correct. I'm pretty sure this fitting is correct, but physically or in reality, it doesn't mean anything because there's no negative cases, right? So you try harder, right? Let's try fitting a quadratic function, ax squared plus bx plus c. It's getting better, but now you still get negative cases. But then all the way you do to a polynomial fitting, it's a super polynomial. Here is the ax to the 5 plus bx plus c. And then you can see that it fits really nicely and almost on top of all the data points, which is very good. Does that mean it's a perfect fitting? I don't know, but we can check, right? So how are we going to check? So this is a concept of regression, right? So now we have a curve that we just did with the 5th order polynomial, and we look at that. So the 5th order polynomial fits the data very well up to day 28 or 29, because started from 0. Right. So you can see that it fits really well before March. No, it's actually not March 15th. It's actually almost the end of March. And now let's take a look at, let's extrapolate the data points to predict what's the total cases at day 40 and day 60. And we got two numbers. One is 88K. The other one is 6 million. Which means that after 10 days, starting from 10 days from now, we will get 88K, almost 0.8 million cases within next 10 days. So that will be triple, more than triple than the cases we have right now. Or that's the US cases, which is a lot. And then if you look at, if it grows like this, the same way as the polynomial function after within another month or after another 30 days, and the total cases will be 6 million. We don't know if it's right, but to me, it's like these numbers are way over predicting the cases because it's just a mathematical prediction. It's a mathematical prediction. There's no real science behind it, right? So the function looks beautiful, but the prediction could be completely garbage. Right. So the reason is that, is this really the right function to predict the future? It's unlikely not true. All right. So now let's take a look at the most realistic functional form to describe growth like this, including population, pandemic, and all these things. It's called logistic function. So a logistic function fx is defined as c divided by 1 plus e to the minus x minus b divided by a. So the logistic function has 3 parameters, a, b, and c. So they all have physical meanings. So a here, which is in the denominator right down here, refers to the infection speed. And in the pandemic crisis, it's also known as the R0 value. Some of you might heard of it. So for SARS, it was about 3. And so the physical meaning is that one patient on an average sense can get 3 other healthy people infected. So that's the A value. And the C value right here is straightforward because you can see that if time goes to infinity, x goes to infinity, e to the minus infinity is basically 0. So the curve asymptotically goes to C. Right? So C is basically the upper limit of the logistic curve, and it's sometimes also called the capacity. All right, so B is also very clear. So B is exactly where the maximum growth speed is. So for here now, after this B point, and then the growth is actually decreased, and you can see that this curve become more flat and more flat and eventually saturate. So B is exactly where the maximum growth is down there, right? So we have all the meanings for this curve A, B, and C, and we can predict that. So let's try to fit the total cases from another country, China, to use a logistic function because it's almost over, right? And we have the data now, and we can go back to fit and to get the parameters. So the step 1, and we filter the data by selecting entity equals to China and date is greater than January 1st. So so we do entity equals to C, which is China, and dt is greater than date 0. So dt is the date time column, and date 0 is the date time object that we specified here. So the second step is we define logistic function, which is very straightforward. It's the exact same as you define the linear quadratic functions like this. So the third one is we use the curve fitting function to fit the total cases. Right? Remember that we wanted the starting time to be 0. So we have a better estimation of the B value down there. And then now we create a new array starting from 0, which has the same size as the total cases. All right, so that's the days, use the arange function. And now we can do the curve fitting, use the curve fit and logistic dot model. So this is the function. This is the horizontal axis, which is days starting from 0 to whatever day it is right now. And from 0 to day since January 1st. And then the data I want to fit is the DFC total cases. And the p-value here is an initial guess. For example, I'm telling the curve fitting function to start from A equals to 3.8, B equals to 40, and C equals to 80,000. And it's optional, and you can also, you don't need to specify it, but sometimes if you don't specify it, the curve fitting fails and gives you 0, and you will see that. Right. So a couple of things to notice, to pay attention to is that the days, what is the days? So days is a NumPy array starting from 0 to whatever days it is now. And also the p-value is useful in some cases when the fitting is really tricky. So the question comes, how to estimate p-value? And for the logistic function, it's really straightforward because we know exactly what the A, B, and C means. Right. So let's come back to the how we estimate the p-value for a curve fitting for a logistic function. And you can see that A here is the infection speed, which is R0. So we usually do A equals to 3. Right? So now let's come back from this curve to the data actually from China. So this is basically the total cases from China starting from January 1st. So January 1st is 0, and up to now it's about 90. And this is the total cases. And you can see that it's almost saturated, and which means that the pandemic is almost over there. So you can see that based on this, and let's estimate A is 3.5. So that's basically based on SARS, and I think that's a reasonable estimation. So the other one is that you can see that at about day 40, and then the curve, on an average sense, it started to curve. And also, there's something happened here because they changed the criteria of diagnostics, but it doesn't change the fact that it's turning. Right? So let's say the center of the maximum growth is 40, starting from January 1st. So B is 40. So C is really easy to estimate. It's exactly where that peak point is. So let's say it's 80K. Right? So now we get P0 equals A equals 3.5, B equals 40, and C equals 80,000. Right? So let's put these curves together, and then we put the p-value here. So this is my logistic function. That's the array for the days from 0 to 90. And the total cases are these data. And then P0 are based on my estimations. And I use the 3.8. That doesn't really matter. Right. So this is the result. And you can see that the blue dots are data points, and the red curve is basically logistic fitting of the total cases in China as a function of time. And it actually does a reasonable job, and you can see that the data points are more or less on top of the red curve. And we can also take a look at the quality of the fitting by print out the peak-off. If you still remember that peak-off coming from the curve fitting function, it's an array of all the covariances between A and B and C. So the diagonal values A, B, B, and C, these are the standard deviation of these fitting parameters. The smaller the standard deviations is, the better the curve fitting is. Right, so let's bring out the variations of the A, B, and C, see what that looks like, right? So if I print out this, and this is the quality of fitting, and you can see print out the P optional, so these are the best estimates, and that's the covariance matrix. And then A would be 4.48 plus minus 0.09. It's a very small value compared to that. And B is about 39.34 plus minus 0.1. So the peak growth is very close to 40. And then the total, the capacity, or C, is 81K plus or minus 256. So that's also a very small number compared to this one. So I would say it's a pretty reasonable fitting. And you can see that looking at the graph, it does a very nice job here. All right, so you can also check other outputs. For example, with the fitting results, we have the cases which is a logistic function, and we can use the diff function from NumPy to compute the deltas between each days, which will be the daily new cases, and compare that with the measurements, right? Because we did not fit the total daily cases, but we can derive total daily cases and compare to the real data and see how good the fitting is. So now let's see, so Y equals to the logistic model days and P opt. So this is the fitting results. And then I'm plotting the diff Y. So I'm using a function np.diff. So the diff function calculates the deltas between two data points and make that as a new array. And then I'm plotting the actual data, but now I'm plotting the daily cases instead of total cases. And if I do that, and this is the result I get. And you can see that I have daily cases fitting, more or less following this predicted value. So this blue curve is basically the predicted value or the fit value. And then the crosses are the actual data. And I'm limiting this curve because there's one data point way over there, which is due to the change of the Diogenes criteria. So in more or less, I would say, this fitting model does a reasonable well job. So the question now is that now you've learned how to fit the logistic curve with your data, and it seems like the curve works quite well. And you're going to ask to practice by fitting the data with other countries. And the question is, are these fitting curves useful in reality in terms of predicting cases in the future? Why or why not? So that's a question to think about, right? All right, so now let's try to analyze the data on your own.